We're going to study the process API today. Can anyone tell me, this is just a review from the previous lecture, what are the different states a process can be in? Ready, blocked, running. So this was the state diagram that we draw to you last time. A process can be running, it can be descheduled, some other process can get running, and if a process is ready, whenever it gets that opportunity, it then gets running. If there is an input output request, you go into a block state, and whenever that request completes, you again are in a ready state. We also saw a small example on the different states two different processes are in. So process 0 starts with running, and since process 0 is running at that time, the CPU can only allocate a single process at a single time. So process 1 keeps on in the ready state. It can execute, but the CPU is not available. As soon as process 0 completes, process 1 starts executing. We saw another example where P0 process was executing, but then from time 0 to 3, but then it requests for input output. So it becomes blocked. It cannot be allocated the CPU at this point of time. And process P1, which was in the ready state during all of this time, can now execute. As soon as process P1 completes, P0 again kicks back into action. It at time t equal to 7, between 6 and 7, it was ready to execute. But since P1 was executing on the CPU, P0 could not execute. We also saw an example. We saw that code which we were running last time. Does everyone remember the process run function that we ran last time? So last time someone was talking about how does randomization work, or what does probability of 10 here mean. So I've written a very small example to illustrate what it means to select input output versus CPU with a given probability. So that is called So it's a very small program. We import the random module, we import the sys module. We take 3 arguments: the CPU length, the probability of CPU cycle, and the length of the input output. So effectively what we're doing is we maintain a count of the number of CPU cycles that have executed, and we want that the number of CPU length cycles should be executed. So we start with 0 cycles. We choose a random number between 0 and 1. If it is less than CPU probability by 100, we increase the count by 1, and we say that it's a CPU cycle. If it is greater than CPU probability by 100, then it's an input output cycle. So the idea is, let's say if the probability of CPU being selected is 100, so random.random will be, it will always be something between 0 and 1, and the RHS here will evaluate to less than or equal to 1, let's say. So this will always get executed. This if condition will always be true, and we'll get all of the CPU cycles. Let's run a very quick instantiation of the program. CPU length is, let's say, 10. Probability of CPU is 100. Input output length is 4. Oops. So since the probability of choosing a CPU cycle was 100%, all of the cycles chosen here are CPU. Let's change this 10 to 0, maybe 1, so that we eventually see some input output and some CPU. You see a lot more input output compared to the CPU cycles. And if we change this to say 50, and if you're wondering why there are so many input outputs even in the probability of 50, because for each input output cycle, we have an input output length. Each time input output is chosen, for the length, IO length, which in my case was 4, we run input output instead of running the instead of giving the CPU to the process. Now, let's say that there was another question on how does random seed affect the choice. So let's just edit the program a little. And let's add another argument. So random seed is basically the seed with which the random function generator is initiated. So what we're using here are actually something known as pseudo-random number generators. Have we studied these algorithms before in some other course? So these are not pure random generators. They use some function. They use x power a mod b, something on that lines. So let's run this and let's increase it to 90. So with random seed 0, we get all the CPU cycles. Random seed 1, we get the same. With random seed 2, we see more input output compared to CPU cycles. Just to show that how randomization is affecting these different runs. So this is also an interesting project idea. So like as we discussed that we can work on some projects in this course and demonstrate them. So one of the project ideas could be to take this program, for example, which the authors have provided, convert it to an easy to understand GUI. So for example, pythontutor.com is one such GUI which takes in a Python code and shows like what is being executed. So can we create something similar for CPU scheduling, which makes it easy to understand what's happening? Okay, so last time when we were talking about the process API, we discussed that we need to be able to create processes. We need to be able to destroy processes. We have to wait for some time, like some process might require to wait till the other process has completed. We require status to know how long a process has run, and some miscellaneous other APIs. So in this class, we'll be discussing about creation of processes using two system calls, fork and exec, and we'll be looking at how we can create how we can wait for a different process using the wait system call. So throughout this course, we'll be periodically referring to man, which gives us the manual for different commands. So if we run man fork, it shows what the system call does for us. So it's one of the best practices to get used to invoking manual command for commands you don't know, for commands and for system calls. So fork, it gives a very good description that fork creates a new process. It gives us what are the preprocessors to include. In terms of description, it says that fork causes creation of a new process, and the new process, which is called a child process, is an exact copy of the calling process. So this is something we need to remember, that the child process is an exact copy of the parent. And there are a few differences amongst the two processes. The child process will get a different process ID, as you would expect, because it's a new process being created. Each process has a unique process ID. The child process has a different parent process ID, which is basically the process ID of the parent. And the child process has its own copy of parent's descriptors. So in this class, I'll be looking at using the fork API, using like understanding how fork works using some of the examples that I've created. So the first task, so I'll build this slowly up. The first thing is how can we get a process ID of a current process. So last time we saw that how we can use the PS command or the activity monitor or the task manager in Windows to look at the process ID of a specific process. So let's see if we can do that within a C program. It's a very simple program. We just use this function get PID, which gives us the current process ID, and we're just printing it out. Let's just compile it to it gives us the current process ID is 73414. Okay, so we now know that in C we can get the current process ID. How can we get the process ID for parent process now? Any idea? So it should be a similar system call, right? We may not know its name, but it should be something on similar lines, right? So the name of the call here is called get PPID, get parent process ID. So you see that it's almost identical. The only difference being that instead of get PID, it's get parent process ID. And it says that the current process, I should have changed. So it gives us the ID of the parent process, which is 38385. Any idea what the parent process of this C program is? Sorry? Any other guess? Operating system, any other guess? Command prompt. The command prompt and terminal, I would say, is the same thing. So it's actually the terminal, and let's quickly see that. So what you're saying is also correct in some sense. It's like eventually it's the operating system, but then the operating system has a child whose child eventually is the terminal. So we saw that the process ID is 38385. Let's just sort by the process ID. 38385. That's ZSH, which is my terminal. So you can have different terminals. In my case, it's ZSH. Or like we saw this in using activity monitor. Can we use the PS command also to find out? But I'm very bad at remembering all the arguments of PS. So let's again look at the manual of PS to figure out how can we, given a process ID, how can we find which command or which process is running. So let's invoke man PS. It has various arguments of process states. A gives display about other users, C, D. So it's the P argument which we need to pass. Displays information about processes which match the specific process ID. See now, so we can get that the command which was run was ZSH and the process ID was 38385. And what if we run this? So we saw that one of the process was allocated. The child process, the current process, the C program, was allocated this ID. What do you think will happen if I run this? It should give me the process which is running corresponding to this process ID. But what do you expect the output to be? It's not running. So let's see what the output is. We don't see anything because the process is currently not running. Okay, so now we look at another variant of it. So let's add some sleep or some delay.
Suppose like when a program stops, so that process ID, that number that is used for the process,
Right.
can be now like given to some other process.
I guess it should eventually be given up, but I don't know what's the policy being used in different operating systems. I guess there would be some buffer period before you would want to give, that same process ID to something and to recycle it, or maybe some implementations say that we never reuse till reboot, and at reboot everything is reinitialized. But then there can be questions, what is the maximum limit we can give to a process ID? Does it go to 2 to the power 32? Does it go to 2 to the power 64? How big a number can we give? All of these questions come up to some based on implementations and also based on some resources that we have. And what's the maximum number of files that we can have open? Does anyone know that? Yeah, just Google that when you go home. So what's the maximum number of files you can have open at a given time in 16-bit systems and maybe in more modern systems?
So what is the profit of keeping it reserved for some time? The process ID.
What is the benefit of keeping it reserved? Since the process has already ended, until and unless that process is being used somewhere else, I think one of the reasons in general could be bookkeeping. So if you are, if you manually logging the process and you're trying to understand what's happening under the hood, I think that's probably the only, for example, how many of us have used the watch command in Linux? So watch command basically would, automatically, let's say if I run PS and I hook it up to watch, so it's basically like rerunning PS every 2 seconds or every 1 second. So let's say I'm using a watch command now to see, let's say I'm doing ls. So I want to see that how many files do I have in a directory, and I'm pushing some files into the directory. So every 2 seconds or so, I want to see the total number of files. So that's how I can use watch. And let's say I'm using watch to monitor the contents of some process or monitor the parent IDs of process or doing something like that. So let's say one of the process ends, another process is allocated the same process ID. So if I'm not aware of the fact that the previous process ended and the new process has been given the same ID, I might be confused or I might be doing something wrong because it's a totally different process now running. So one of the reasons we couldn't see this process on the PS command as well as the activity monitor is that it ended very quickly. So one of the ways to make processes end slightly slowly is to add some delays. Let's add a very simple delay sleep command. So the process will sleep for that number of seconds or microseconds or whatever the API is. Fork them off. So nothing huge, nothing big difference in the previous program. We just add a sleep call here. Okay, so now we can see that the process ID is 74281. And let's see. So we can now see this process on PS by the PS command. And we can also see it on the activity monitor where we can get more details of it. So it's basic. So if you see that it's telling me that the parent process is ZSH, can give me various statistics about the false context switches, open files and ports. And if I just want to have fun, I can look at the parent process of this. The parent process of ZSH is login. The parent process of which is the terminal. which is the launch daemon, the kernel task, and kernel task 0. So this was invoked when the system was booted up. And it's been running for, I don't know what total amount of CPU, the time of CPU has been used. I don't know whether it's 12 days, 53 hours, or 12 hours, 53 minutes, 10 seconds. Okay, so enough of fun at looking at what's the process ID. Now let's actually use the fork command to create a child process. Okay, so this is the code for showing the how to use a fork, and I'm including uni.std.h. So this is just a regular int main. I'm initially printing out the current process ID, which is the process ID of the parent process, and I call the fork command, and its return is int rc. Does anyone know that what rc could stand for? So there's no universal answer to this. Like, it's generally being used, and I was also like questioning this, and I was reading on Stack Overflow. Some people said that this might stand for return code or something on that lines. So what is the return code when fork has been called? Now there are three different types of return codes of fork. One is if it's a negative. So negative return code means that fork has failed. This could be due to various reasons. It could be there is not enough resources on the system. Maybe too many files and ports have already been opened. If the return is a 0, it means that a child has been created. So basically, the child process will return a fork of a return code of 0, and then we can get the process ID of the child. So it's a new process being created, and what happens is the parent is passed the return code of the child process. So three cases. RC less than 0 means that fork has failed. RC equal to 0 means that child process has been created, and it can now it gets a different process ID. RC of any other value is actually the process ID of the child. So that's three different returns for the fork call. So eventually, if this line will run, we'll see that the parent of RC is the return code of the child. So parent of the child process is get PID, which is the current parent process. Let's just run this once to see what we get. So we see that the current process ID is 74731. Then this bit runs, and then the child bit runs. So this might be a bit confusing, what's happening under the hood. Like, how can a single program have multiple, RC values? So that's the whole fun of fork command. It creates an identical copy of the current process, which is a child process. For the child process, RC will be 0, whereas for the parent, the RC will be of the child process. So it's slightly weird, but that's how it works. So let's now look at another variant of this simple program. We'll add sleep into this so that we can see this program on the activity monitor. Any questions, any doubts? So if you could just wait for 3 minutes. I'll come back to this with a graphical explanation also. So this is the same program as the previous one. The only difference being that I'm adding sleep in both of these, so that I can I can view them on the via the PS or on the activity monitor. I'll directly run this Fork demo 5. So do you see this now? So when I'm searching for fork, I see two different processes, both of which have the same process name. So it's an identical process being created, but the process IDs are different. And for this process, the parent process is fork demo 5 with this process ID. So firstly, this thing ran. It then invoked another child process, another copy of itself, which is the child process, for which the return code is 0. Okay, so let me run this again, and let's look at this using the PS command. So the child process has the ID of 74948. So we can get information about this process, but then we can also get information about its parent ID and its own ID also. So -O is allowing us to print various things using a given format. So we can see the parent process ID and the process ID. So now you can do you can think of one fun thing, that if I start from one process, can I eventually trace back to the the operating system kernel, the first thing which was run. So I wrote a very simple program to do this. So basically what we need to do is to recursively invoke this command. So we pass this command the current process ID. Using that, we can get the parent process ID. Using that, we again call this function to get the parent process ID, and so on and so forth. Okay, so this is the program which I wrote. So the first, so the argument it takes is a process ID. So subprocess.check output is basically running this on behalf of the current Python program on the shell. So it's running PS minus P, which is PS given a process ID. And then we're trying to figure out the parent process ID. We do a tail -1 to get the last line because we don't want the header. We could do it some other way also. And then there is some, byte to string conversion and decoding stuff, which we don't need to really bother about. So if we run this, let's run this again. The child process has the ID 75302. So we see that 75301 has the parent process ID 38385, which, if we remember, was the process ID of ZSH. And this is of login, this is of some other thing, and so on and so forth, starting with 0. And this PPID is just because I think it's entered in an exception. So it's after process IDs, before process ID 0, nothing existed. So tail -1 doesn't give us, tail -1 gives us PPID instead of giving us the correct number. So now coming to a question of what's exactly happening under the hood. So we have a parent process which has a main function where somewhere down the line we're calling the fork function. So this process has an address space, which let's call the address space of the parent, which has the code, static data, heap, and the stack. So does everyone remember that there are 4 different parts of the address space? So the program counter will eventually reach main, and that's when this program execution will start. So let's start at main. Now when you call the fork, And let's just zoom out a bit. So another process will be created, which is now a child process, which is an identical copy of the parent process. There are a few differences. Firstly, the the child process, it will start executing from fork onwards. So it won't start executing before that. So anything you've done before that, as such, need not be redone. But this is a question we'll see in the lab tomorrow. Like if we had initialized some variables before main, does the child process get an access to those variables or not? So that's something we look in the lab tomorrow. And now, once the child process has been created, it gets its own address space. So whatever happens here does not uh, have anything to do with what's happening in the parent. Although now they are exact identical copies.
So,
Yeah.
so with the child function, like child process again inform the fork function.
No, so it will start executing after the fork. So after the fork has been executed, so you've got a return code, and that return code is now passed.
So
So
that's why in the earlier program it was printing twice, like two of the sentences.
two of the
Like
sentences,
in the if else case, the condition.
right? So
Comment, like it was printing two sentences.
right, so it was printing out two different responses. So it's printing out the if condition, sorry, else if and else, both of them. So let's look at the code again. So once this has been executed in the parent process, now both the parent and the child won't will flow only downwards in flow. For the child, an exact copy has been created, and after the next statement for the child, the RC is 0, return code is 0. So child will print out this, whereas the parent, for the parent, the return code is the process ID is the child, and then this statement is executed in the parent. Is everyone clear with this? Okay, so if we really want to have fun, we can actually go and see the source code of Linux because it's online, uh, online available on GitHub. So if you want to search, you could just and in this you could search for, let's say, fork, and you can see that there are 418 instances of usage in C, few in its assembly, few text, few C++, one in Perl also. And let's say if you want to look at C, so you see something like architecture Spark include ASM syscalls. So if you're the curious type, you'll go on GitHub and see what are different architectures. Any ideas on what different architectures would Linux be running on? One is Spark. X dash dash. What do we use? 86. What else? What does Raspberry Pi run on? ARM. So let's go on Linux architecture. So you've got ARM, you've got ARM 64, you've got Hexagon, IA64, MIPS, PowerPC. So it's not being used so often these days, but PowerPC, Spark, x86. So it's always fun to understand that for different architectures how stuff is being built. Now, one of the problems of the previous program was, so I don't know if you noticed or not, in some of the runs, the child executed first and then the parent. In some of the runs, the parent printed out before the child did. Did anyone notice? The parent executed before the child, parent before the child, parent before the child. Okay, so for some reason it doesn't want to show you the non-determinism here, but maybe if you run 1,000 times, sometimes at least you'll see that the child executes before the parent does. Now this is an issue because we want some determinism in the way the code runs. So we ideally want the child to finish his processing before we give back the control to the parent. So one way to do this is we discussed about the wait system called. So we'll wait for the child to finish executing, and then we'll give back the control. Then the parent will again resume execution. So let's say that again, as we discussed earlier, we are running Adobe Illustrator. The parent process, which is the main Adobe daemon, it creates all of these sub-processes. It creates these other processes, let's say for initializing the toolbar, for initializing the color palette, for initializing other stuff, for initializing fonts. Now you want to wait for the completion of the children process before you want the main thread to be running, the main process to be running. So, so this is just for illustration purpose. Maybe they're not using different processes but threads, but just get the just get the drift. So we can again go and you just look it up on the manual. What does wait do? Oops. So this does not look like what we saw previously, right? This looks like more like a Unix command than a C thing, right? What if we did man to wait? This looks similar, right? So what's happening? Like, why did man work previously for fork, and why not for this? So in fact, for fork also, what was running was man to fork, and if we are to do man one fork, we don't see. So manual has multiple entries. Section 1 is the Unix commands. Section 2 contains these C system calls. This is something I discovered yesterday. I also didn't know about this. So it wants to have this preprocessor sys wait.h, and it says that wait suspends execution of the calling process until the stat log information is available for a terminated child process or a signal is received. Yes, you can also look at this manual online, which is showing us man 1 on the left hand side and man section 2 on the RHS. That's why man fork didn't show us anything. Let's run wait demo1.c now. So it's starting from the same process, from the same program that we did previously. But the only difference here being that in the parent process, now we have added wait for null. So it's basically waiting till the point the child process is executed. And now it will have a deterministic order of execution. So let's just run this and see. Okay, so it also added sleep in the child just to show that. So now it's always this order that the program will execute. But if you notice, I didn't include any preprocessor which was suggested in the wait manual. So it's suggested using sys wait.h, right? But I've not used it here. The program still works. So I was again curious on why this is happening, and I was again looking it up on Stack Overflow, where it said that it's always better to use sys wait.h. That's as per the standards. So the other program is it's just the same program, but we now have the correct preprocessor, sys wait.h. It will give us the same result. Maybe there are some boundary conditions where the two differ. Okay, so instead of wait null, if I wrote wait 1, will it run or not? So many of these things you'll have to actually look up on the manuals and also to look at what are the arguments made. What's difference between null, 0, and string character of null basically, like backslash and 0. Is there a difference between them? This is something, just for fun you should look it up and see just by experimenting what do you get. So if I wrote wait 0, will it run? If I wrote wait null, will it run? If I wrote wait 1, will it run or not? Okay, the final system call we'll be looking at today is exec. So previously we looked at fork. So one of the obvious limitations of fork was that it only creates a copy of the parent process. Now, it may be useful in a lot of cases, but eventually we want to execute or we want to create new processes. So for that we'll be using the exec system call. So if you notice, I wrote here man3 exec. Just find out on your own why man2 didn't work or man1 didn't work. And it says that it's used to execute a file or a process. The important thing to note here is actually the description is fairly verbose and actually really good. So it says that the exec family of function replaces the current process image with a new process image. So this is something we need to really remember. It replaces the current process image with a new process image. So let's say if I'm executing something, if I'm running a normal C program, I invoke exec now. Let's say I was running hello1.c. I do an exec and I call hello2.c. So now hello1.c is no longer executing. It's hello2.c which will be executing. And the entire image will be of the process will be replaced by hello2. So we'll again look at some demonstrations for this. So this is a very simple first cut on understanding how exec works, and we'll be using a specific exec variant called exec VP. We just have a int main. We defined the command which we want to execute, which is I want to execute hello.out, and I'll give it. I'll just give this command as an input to exec VP. The second argument here is the set of arguments that you would give. So I'm passing hello.out without an argument, and this line of code will not actually execute. So why will this line of code not execute? Sorry, one person. Right. So because the process image has been replaced by the new process which is executing. So in this case, the process image of exec demo1.c will be replaced by hello.out. So it won't. That's why it won't execute beyond this line. Yeah.
So usually in functions, they return some value, right?
They usually return some value.
Like if you run exec, then the return value from like run, right? So will it give you a method?
Let's see. What does this thing return? If any of the exec functions returns, an error will have occurred. So basically this is a special type of function which should not be returning in an ideal case. If it is returning something, then error will have occurred. So you could build a more robust program by looking at if something is returning or not, and then executing it. Right. Yeah, for most of these questions, like you'll have to actually just look at the manual to get the answer, and then just try out some programs. So if I just execute this exec demo1, so I see something as hello there x equal to 10, which is nowhere in this program. And if I look at hello.c, so it just prints out x equal to 10, right? So basically I created an I wrote a program hello.c, converted into an executable hello.out, which was then executed using this exec demo 1.c, the executable of that. And because the process image has been replaced, so this line I will not execute as actually not executable. Let's look at another variant of it. So we're running now hello2.out. We are passing it in two arguments, and the final argument. So we basically, if you look at arg of 0, 1, and 2, so it's an array which we have created with the different arguments we want to pass to hello2.out. Let me, in fact, first run hello2.out to illustrate. So it's a simple program which just gives me, let's say, which prints out the first argument, and it has some local variable which prints out x equal to 10. You can see the code of this also. So it looks at the first and the second argument. The first argument is the name of the process, and the second argument is what's being like the first actual argument being passed in the value. So we, in this program, we are running hello2.out with two arguments, 10, 20, and then with null terminating the set of arguments. And of course, so the previous example we showed that how we can create a process using exec, but we were not passing any arguments. In this case, we are doing the same, but with the addition of arguments. So if we run this exec demo 2, so we see that now this program is basically being executed with different arguments. And just for completion's sake, let's just edit this. To create some other argument. See, so this is a set of argument being passed on to the second called process. So I think we're just out of time. Maybe we have a couple of minutes for any questions we have till this point. We'll resume from here. We'll meet in the lab tomorrow at 4. And just get your laptops if you want to. We'll pass on the virtual, the VM image tomorrow.